Hi everyone. For the continuation of the water treatment and technology, now we will discuss the flocculation. Whereas rapid mix achieves successful mixing of the water and the coagulant, flocculation provides the conditions necessary for optimal particle growth so that sedimentation can occur successfully. The objective of flocculation is to allow the particles to collide, adhere to one another, and grow to a size that will settle readily. Mixing must be sufficient so that when collisions occur, they have enough energy for the particles to stick together. On the other hand, too much mixing can shear particles, they break apart, and the resulting particles will be too small for sedimentation to occur effectively. The major design parameter used in flocculation is the velocity gradient, g. This parameter describes the degree of mixing, and the higher the g value, the more vigorous the mixing. Now let's move on to the upflow solids contact. Mixing, flocculation, and the clarification may be conducted in the single tank. The influent raw water and chemicals are mixed in the center cone-like structure, so the solids flow down under the cone, sometimes called a skirt. So this is the illustration of the upflow solids contact, where there are three zones: Zone A, Zone B, and C. Zone A for rapid mix, Zone B for the flocculation and solids contact, and the Zone C is for the upflow and sludge blanket zone. Ion exchange softening. Ion exchange can be defined as the reversible exchange of an ion on a solid phase with an ion of like charge in an aqueous phase. In water treatment, ion exchange is the most used for metal removal. Because of its simplicity, ion exchange is most commonly used for in-home water softening systems. So some large water treatment facilities use ion exchange softening, but the most common application is for the residential softeners. The ion exchange material can either be naturally occurring clays called the zeolites or synthetically made resins. So the several manufacturers produce synthetic resins. The resins or the zeolites also are characterized by the amount of hardness that they remove per volume of resin material and by the amount of salt required to regenerate the resin. So here the reaction can be represented as shown below, where R represents the solid ion exchange material. By this reaction, calcium has been removed from the water and replaced by an equivalent amount of sodium, that is 2 sodium ions for each calcium ion. So in this reaction, the alkalinity would remain unchanged because there is no reaction or exchange of anions. The exchange results in essentially 100% removal of the hardness from the water until the exchange capacity of the ion exchange material is reached. So when the ion exchange material becomes saturated, no hardness will be removed. So at this point, breakthrough is said to have occurred because the hardness ions pass through the ion exchange adsorber. So when the effluent hardness concentration exceeds a predetermined level, breakthrough is said to have occurred. At this point, the ion exchanger is taken out of service and the ion exchange material is regenerated. So let's solve a problem related to the ion exchange softening. A home water softener has 0.1 cubic meter of ion exchange resin with an exchange capacity of 62 kilograms per cubic meter. The 4 home residents each use water at a rate of 400 liters per day. The well water they are using contains 340 milligrams per liter of hardness as calcium carbonate. It is desirable to soften it to achieve a total hardness of 100 milligrams per liter as calcium carbonate. What should the bypass flow rate be? So the question is asking for the bypass flow rate. Okay, let's solve. So the first thing we're going to do is draw an illustration. Say we have here an ion exchanger. Okay, this is an ion exchanger. So the mass in, or the flow rate in, we have here the volumetric flow rate total, then the concentration, initial, and the mass out here, the volumetric flow rate total, and the desired concentration. So it states here that there is a bypass line in the ion exchanger. So let's draw a bypass line here. And this is the flow rate for the bypass and the concentration for the bypass line. And this is the volumetric flow rate out, and then the concentration of this outlet line. So we will have a material balance on this region. Now for the material balance, we have the volumetric flow total is equal to the volumetric flow of the bypass line plus the volumetric flow of the outlet. Next, we will have the component material balance for the concentration. Okay, so for the concentration, we have the Q out, or the volumetric flow of the outlet, times the concentration of the outlet, plus the volumetric flow of the bypass times the concentration of the bypass line. So it states here 340 milligrams per liter of hardness as calcium carbonate is equal to the volumetric flow total. It states in the problem that the 4 home residents each use water at a rate of 400 liters per day. So 400 liters per capita per day, and then we will multiply by 4 capita for the 4 residents times 100 milligrams per liter as calcium carbonate, since it is the total hardness. So 100 milligrams per liters. Assuming that 100% of the hardness is removed, so the concentration of the outlet is equal to 0. So we will just cancel these out here. So the remaining is the volumetric flow of the bypass and the volumetric flow total. So for the volumetric flow bypass, we have 470.60 liters per day. Okay, so this is now our final answer. Now let's move on to sedimentation. Surface water containing high turbidity may require sedimentation prior to subsequent treatment. Sedimentation basins are usually rectangular or circular with either a radial or upward water flow pattern. Sludge that is withdrawn from the bottom of sedimentation basins may in some cases be discharged back to the river. To reduce the turbulence caused by the rushing water as it leaves the tank, a series of troughs called weirs are put in place to provide a large area for the water to flow through and minimize the velocity in the sedimentation tank near the outlet zone. The weirs then feed into a central channel or pipe for transport of the settled water. These are examples of the sedimentation basin. So we have here an empty sedimentation basin and a full sedimentation basins. If you observe, there are a lot of components below this sedimentation basin. So determination of the settling velocity. Settling properties of particles are often categorized into one of 3 classes. We have the type 1 sedimentation, type 2 sedimentation, and the type 3 or zone sedimentation. For type 1 sedimentation, it is characterized by particles that settle discretely at a constant velocity. So they settle as individual particles and do not flocculate or stick to other particles during settling. So examples of these particles are sand and grit material. For type 2 sedimentation, it is characterized by particles that flocculate during sedimentation. Because they flocculate, their size is constantly changing. Therefore, the settling velocity is changing. And for the type 3 or zone sedimentation, the particles are at a high concentration, greater than 1000 milligrams per liter, such that the particles tend to settle as a mass and a distinct clear zone and sludge zone are present. So for the determination of overflow rate, in the case of type 1 sedimentation, the particle settling velocity can be calculated and the basin designed to remove a specific size particle. Sir George Gabriel Stokes in 1845 found out that the terminal settling velocity of a sphere falling under quiescent conditions could be described by the following equation, shown below. So this is the formula for determination of overflow rate. Now for filtration, as the water flows over the weirs and exits the sedimentation tank, it still contains particles that were too small to settle or somehow escape removal due to fluid patterns. Filtration is the process by which water flows slowly through a bed of granular media, usually sand, anthracite, or garnet. So some of the industries are using the combination of these filter media, the sand, the anthracite coal, and the garnet. So as the water passes through the medium, particles become trapped due to several mechanisms: interception, flocculation, straining, and sedimentation. The densest particles are strained like spaghetti. These particles are simply too large to pass through the pore spaces of the medium and become trapped in the upper depths of the filter. The particles flowing at a sufficiently low velocity are intercepted and attached by weak electrostatic forces to the filter medium. So the filters can operate as either slow or rapid sand filters. Slow sand filters conventionally use only sand, but rapid sand filters use a variety of media. Single medium beds use only sand, but dual media filters use sand and anthracite coal. So the mixed media beds use coal, sand, and garnet. Rapid sand filters are cleaned in place by forcing water upward through the sand. This operation is called the backwashing. The wash water flow rate is such that the sand is expanded and the filtered particles are removed from the bed. After backwashing, the sand settles back into place. The largest particles settle first, resulting in a fine sand layer on top and a coarse sand layer on the bottom. So this is the typical cross-section of a rapid sand filter. It has an inlet main, a wash water outlet, and the water troughs. In some industries, it is called the underdrain. Then we have the graded filter sand, the graded gravel, and the perforated laterals. In the future, when you work at the water treatment plants, the standard for designing this equipment is in accordance to AWA, or the American Water Works Association. So that's all for now. Thank you.